Hello everyone. In this video we are going to talk about rigid dynamics analysis, and at the end I also show you how you can analyze moving mechanisms and moving rigid bodies and allow a few of them or maybe all of them to be flexible so you can calculate the stress in them. When you say rigid body, it means that the object is basically infinitely stiff and it does not deform. So basically the nodal displacements for any node is zero, and due to the deformations, not the displacement, the displacements due to the motion are directly governed by the equations of motion of the Newton equations, but there is no deformation in the object. So here, to demonstrate that for you, I have chosen the slider crank mechanism, and to make life simpler, I avoided pins at these 3 revolute joints to make it easier, but this is properly constrained in SolidWorks, and it is exported as STEP, a step file, so I can bring it into ANSYS. So here I imported it into this geometry, and then I connected it into rigid body dynamics, right? So here, if you go, you can grab one of these rigid dynamics and bring it here. And then once the geometry is set, you double click on the model. So this is your model here. And now I'm going to apply some rotational velocity at this joint, and I'm going to measure all sorts of entities from accelerations, positions, velocities, forces, and so on at all these different rigid bodies. So right now, every object is assumed to be rigid. And these are your objects, right, that you brought in. And you can give them any material assignment that you want. So for the moment, to just simplify it, I assume that they are all out of structural steel, make life easier on us. Okay, and then we are going to go from there. So right now the geometry is good, and you see all of these objects, if you look here, they're all rigid, but later I'll show you can change them to flexible. Not of course in this environment, in the transient structural analysis you cannot change them to flexible here. So these are your objects, the material is set. The first thing you do is you go to connections, and here automatically it made some contacts for you. I guess these are from the previous times that I did it. So when you typically bring them in, it might have some contacts for you here, some bonded contact or something between the objects. Make sure if there is anything under this contact, you get rid of it. Okay, so you clean up any kind of contact that is under connection. You first clean it up, there is nothing. Now start creating it. So what you want to do is, under these contacts, you go to joints, and then here you first fit here this body, this base to the ground. So you go body to ground, fix. Then you choose this entire rigid body, and then you apply that. And if it asks for scopes, basically the surfaces, here I choose this one and this one to basically show that these are the areas that are not going to move. Okay, so that object is now basically glued down to the ground. The next things you want to do, you have 3 revolute joints at these 3 positions between the ground and the crank, between crank and conrod, and between conrod and the slider. So you go to joint and you go to body, and then you go to revolute. And each joint that is not between the ground and another object, between 2 objects, it has a reference point and it has a mobile body, or a reference body and a mobile body, and you can choose which one. So here, since I want to go for this, my reference body is going to be this object, so I just click on it, and then it shows me other surfaces that I can choose. Or I can go here, you see it says reference, I click on the scope, and the surface, the area of the revolute joint that I want to choose out of this object is this surface and this guy, right? These are the revolute portions of the ground. And I apply that, and then you go down, and here are the revolute surfaces of the crank. So I choose this one and then this guy, and I apply, right? So now I have a revolute joint between these two, and you can see these objects here, okay? So if your assembly is too busy, when you click on one of these objects, you can see them on the side windows, and then you can go exactly and choose the surface if it's not so clear. So here I remove the pins, so there is nothing to prevent me from seeing these surfaces and choosing them. But if there was a pin here, the way that I go about it, I go in this window. I go in this window, and in this window, since only that object is shown, nothing else, I can easily select the surfaces, because then the pin is not going to be shown here. So the next thing is, as I said, another revolute joint that I need, and that is between the crank and the conrod. So again, I go down here, and for my reference this time, I choose the crank surfaces and apply, and then for the scope of the mobile body, I choose the surfaces of the conrod, these two, and apply. So that's my third one. And finally, I come down here and do the last revolute joint body to body. So again, down here, my reference body is going to be basically the crank. Apply that, go down, and then here I choose this one and this one. And as I said, you can see them here too, right? So you can choose them from here if you like. You can choose them from this window, right? You can choose them here and apply that. So now the revolute joints are all in. The last thing I need to do is a translational joint between the slider and the ground. So I go to joint, I go to body, body, and this time I use a translational joint. Look at all these different types of joints that you can apply. So I go a translational joint, and this time my reference object is going to be this surface on the body, on the ground, and then the mobile surface is going to be this guy. Now look here. I cannot see this bottom curved surface of this object to select, right? Because it is on this red surface, so I cannot see it, right? So if I want to select that surface, what do? I choose this, I click on any face, it doesn't matter, just click anywhere. So the mobile object appears here. And now look, I rotate it, and instead of that surface, I choose what? I choose the bottom one. So I choose this one instead. You see? And apply that. So if it's not visible, if the surface you want to choose is not visible in the assembly, it should be visible in the mobile body or reference body views. So now I got all of my 5 joints, and then I go ahead and create a mesh. And if the mesh is, you see here it says the mesh control is not associated to any geometry. So here it needs a body sizing and it needs some geometry. Yeah, last time when I was working with this before starting the video, I already added the body sizing. This one is typically not there. Okay, so it's like this basically. When you come, it's like this. So when you say mesh, ideally it should be able to generate some mesh for you, but the mesh is not good. The mesh is not fine enough, especially for the second part where we allow one of the objects to be flexible. So what I did was I inserted a sizing, and for the objects to select, I chose the body and I chose all of my objects, and I applied some smaller mesh size to them, which is like 14 mil. I changed it to 4 mil and made it a little bit smaller. Okay, so I meshed it, as you can see, there we go. And now it's time to apply motion. And let me get rid of this as well, which is I added earlier. So now you want to create the inputs to the system. And it can come from the motion of this object, or it could come from the rotational joint here. So I start motion here and I get my output from there. So I right click on the transient, I go to insert, and I add a joint load. And it says what joint, so I say I want this first revolute joint, and it highlights it for you here. Then it's a rotation Z, of course, and it says what type is it? Is it a rotation, rotational velocity, acceleration, moment, or something? I say I want to apply a fixed rotational velocity, and it says what's the magnitude, and I say, let's say 20 radians per second. Okay, so now I have a constant 20 radian per second angular velocity applied at that joint, and that's enough for me. If you want, you can add anything else, right? You can go ahead and add, let's say, standard Earth gravity, for example. If you want, you can add that or anything else, right? So there are some loads, not all types of loads, that are available for you. Joint load, remote force, right? Loads and so on. They are available, and here you can change it to moment if you want to. The other thing, I go to the analysis setting, and this time by default when you start is 1 typically, but here I want to see the simulation for 5 seconds, so I change it to 5. And the other thing I can do is instead of making this rotational velocity to be 20 from beginning to the end, I can create a table of data and make it to go up gradually, right? Or I can keep it constant. It's up to me how I want to define it. So here, I right click here when it says magnitude, right? And I can choose it to be tabular. And this is the table. So I can give it some numbers. So in second 1, I want it to go, let's say I want it to go from 0 to 20. So first go to maybe 4. In second 2, go to 8. Let's see, in second 3, go to 12. Second 4, go to 16. And finally, in second 5, go to 20. Okay, so I make it linearly go up. So I can do it however I want. And then in the solution, I can insert. There is deformation, but that's not what you want most probably for a dynamics analysis. You go under probe, and you say, well, I want position. And it says, fine, position of what? And you say, well, the position I want is this object, this block, or maybe a point on it, or maybe an edge. It doesn't matter. So I want this surface, and apply that. And then here it is going to give you all of the results x, y, z, but what you really would need is x velocity, because this guy is only moving along the x direction. Right, you see here it says results all. If you want, you can change it. You say, hey, I only want x-axis. So if you don't want it to do a ton of calculations for you, just limit it to what you want. And so now what I can get is basically the position of this guy versus time. But maybe you need more stuff. For example, you right click, go here, go to probe, and say I want angular linear velocity. And again, you can choose this surface and apply that. Right, and again, you might just choose x velocity, right? So now you can look at the velocity of the slider versus time, or acceleration of that, or anything for that matter, right? So let's say acceleration of that versus time. Or you know what, let me choose something different this time. I choose the angular acceleration of the crankshaft, the conrod, I'm sorry. So here I go to angular acceleration, and it says angular acceleration of what object, and here let me see if I can get this guy and apply that. And again, since everything is spinning about z-axis, so I say only z-axis, right? So I can plot alpha of this versus time, or anything that you want, right? You might say, what about the joint forces? Can I find the joint forces or anything like that? The answer is yes. For example, let's say you want the moment or the joint force at this pivot here, right? So how would you get that one? So that joint is this guy here, this revolute. So grab it and drag it and drop it onto what? onto the solution here. So drag that joint, bring it onto the solution and drop it. And then it gives you something called a joint probe. And this joint probe, there are lots of results associated with it. So if you go here, you see the results is total force. But if you want, let's say I want the constraint force, I want the total moment, I want something else, right? The constraint moment and so on. So let's say I want the total force, right? And then change this, let's see. Here, I can do all, which is X, Y, and Z. Let's keep it that way. And I can rename it and call it the crank pivot crank to ground pivot force, right? Or I can do another one here. I drop it here. And this guy, this one, I change it to moment. And I call this guy crank to ground pivot moment or moments, right? So when I get all of the things that I want, then I go ahead and solve. And it should not take a lot of time as long as it's all rigid bodies. It should be relatively fast. Okay, and you can get all of those data that you want, and those are the things that you calculate in a dynamics course or machine design or anything like that. So here, this is the position of basically your your slider versus time, and here there is another slider here, right? Which wherever you click, it shows you the data for that. And not only that, there is another interesting thing that you can do is, let's say it's this data here, right? You right click there and say retrieve this results, and look what happens to the geometry. You see? So you can take this wherever you want, or you can right click wherever you want and say retrieve this results for me. And it takes you to what? It takes you to that location. So this is an interesting tool. Let's go here and retrieve this one. There we go, right? Or bring it to the beginning and retrieve this one. So there are all sorts of things that you can do. And this is your animation, by the way, right? Clearly you see this is your mechanism animation. And this is the velocity probe, right? Now clearly you see your velocity is increasing. Why is it increasing? Because your joint rotational velocity is increasing. You're going from 0 to 20 RPM, linearly increasing it, so everything would increase with that. This is your angular acceleration. This is the crank to ground pivot force, right? These are all different forces. And if you don't want all of these forces, like if a force is very small, you can just simply go ahead and what? Go ahead and turn them off, right? Like this one is all 0, so you can just shut it down. Or if you just want the total force, so go ahead and get rid of the forces that you don't want. For example, this was Z that I turned off. Maybe I don't want to see Y, maybe I don't want to see X. I just want the total force, so you can see that as well. Or this is the moment. Again, you can just turn on or off any of the things that you want to see. Like this. Okay, so again, note that here I'm increasing my angular velocity. So if it's like from the beginning 20 all the way to the end 20, then of course the results are going to be steady. I'm not going to get variable results, right? So let's see. Okay, so this is the position, right? And you see it's completely stable. Nothing is increasing with time, right? This is your velocity probe. This is angular acceleration. These are your forces, right? You see the total force versus time. This is the total moment versus time and everything like that. So you can get lots and lots of useful results out of this rigid body dynamics that you have over here. All you need is, as I said, is to go ahead and define your joints, define the joint loads, and then you can go from there. Now, whatever angle that you export your mechanism, when you export it to a step file, let's say in SolidWorks, your initial condition, your initial angles for ANSYS are going to exactly match these angles. So if I export it at this angle, when I save it like this and export it, when I bring it into ANSYS, this is going to be my initial condition, right? If I don't want that, then I can change it to another configuration and then save it, right? But when you bring it into ANSYS, can you change your initial condition? The answer is yes. So if you look at this position, right, your initial condition is here. See if I can retrieve this results for you. Here. You see that exactly match what I had here. It was like this. So, but you have the option here to change the initial angle and the initial position if you want to. So I can go ahead here to the joints, right? And let's say I want to change this joint. So I click on this revolute, and then I go here under joints, and then I use this option which says configure. Or I want to move the slider, I go to the translation, I go to joint, and I use the configure button, and then this guy here gives me an access and allows me to basically change my initial condition to whatever I want. So now I'm going to start from here, okay? So just wanted to show you this configure joint as one of the options that you have. And one other thing that you might say is, what about the rotation angle? If I want the rotation angle of this joint, so what I do is I grab that revolute joint that I want the angle of it, and I drag it and drop it under solution to give me a joint probe. And so now, instead of the total force, I'm going to measure the relative rotation about the z-axis. And let's see if I can retrieve this result only. There we go. So you see clearly the angle is increasing linearly. And now if I want, I can plot this joint. Let me rename it to crank angle. And I can plot this position versus the crank angle, right? So I grab both of them and I go to the chart. And then the x-axis, I change it to be the crank angle. And I'm not gonna show time. Double click and turn it off. And now clearly, as you can see here, is the position of the slider versus the angle of the crank, right? Millimeters versus degrees. So this is what you can do for a dynamics analysis, right? And you can export it as a report, and this can be what you really need for rigid body dynamics analysis. Now, if you want to look at the stress in the members, what you need is a transient structural. You cannot do it in rigid bodies. So you grab a transient structural and you grab the engineering data, geometry, and the model. You copy them into this guy, and now you can go ahead and inside this, you can change some of the members or all of them into flexible members and look at the stress in them. And transient structural, I'll make a separate video about it. Okay, and here the equations are way harder. They are time variant, and they are way harder to get a convergence on the solution for them. So many times you'll see that, hey, it's not converged, and you have to reduce the time steps, you have to apply finer mesh, and the transient structural, as we'll see, is much more sensitive. So here, these areas that you have the question mark, you have to go and fix them. So initial condition is good, analysis solution. It is asking you for a time steps. My total time is 5, so here I go 1 second, and hopefully that's small enough. Here we go to the solutions, and we can add whatever we want. Let's say we want stress 1 mises, so we add that, or we want deformations, we can add that. What I need is, I need to grab this input motion from the transient analysis of rigid body. I need to copy it under transient of structure analysis. So I grab it and drop it down here. So now I have the same input motion for here. And the other thing I need to do is I need to go under geometry, and these objects, whichever one I want flexible, I need to change it. So the support, which is the ground, I can assume, let's say it's rigid. I don't care too much about it. Even the slider might not be a big concern for me. Maybe what I'm really concerned is the crank and the conrod, whether I can basically set them flexible. So I click on them and change this rigid to flexible for them. And then the other thing is your mesh has to be absolutely a fine mesh here, right? So you might need to bring down the sizing. So I bring it down to 2 mils. And the other thing is your time steps. And if the loading is a fast changing load, you need to change that. So here, my rotational joint velocity is 20. It's not a big thing, but just to get a convergence, I bring it down to 2 instead of 20. Of course, it's not going to create much of a stress, but hopefully the solution will converge. So now let's see if it converges. If it gives you warning, it's okay. If it gives you error and say it didn't converge, you see, then that's not okay. So let's see here. I got a couple of warnings. See if I get error. No. Yeah, but it did not really converge for me. You clearly see that it did not converge. And if I look at the messages, yes, here, you see, the solver engine was unable to converge. Okay, so this time I changed a bunch of things to allow me to converge. What were they? The first thing I did is, first I only made the crank flexible, and I removed the conrod flexibility, just let's say crank. And the other thing is I increased my rotational velocity step by step. So I did not go from jump directly to 2. I linearly increased it from 0 to 2 to allow me to allow my equations to converge into each one of their own loops, right? Because it's a numerical solution and they are done all in loops. I got rid of a lot of extra things that I had from the rigid body, all of these transient ones from the rigid body, the charts, everything to make the calculation simpler. I went down here and the update, update interval, I just did it 1 second, although it's not really affecting my solution. The biggest thing I would say is I reduced the number of rigid, flexible bodies, and I increased my load very gently. Okay, that's what I did. So, and here, if you just do these two, hopefully it is going to just give you warning and converge, as it did for me. And also on this stress, I made sure that I only select the flexible object, which was the crank, right? And now you clearly can see that. Here we go. These are the stress in the cranks. Now, of course, they are small. If you look, they are like 3 kilopascals, right? The maximum. And the reason is the maximum joint velocity I have is 2, the RPM. The rotational velocity is 2 radians per second. Now, if I go ahead and just change this, make it like 10 times bigger, right? So I just go ahead and change these numbers to 10 times bigger. Gradually increase it, but go up on scale. Let's see if I still can get convergence. So how fast your equations are changing versus time, that's the thing. You see, the solver engine was unable to converge. So as soon as I made my system rotate faster with the settings that I have, it's not going to converge. So we're going to talk more about this transient structural analysis, because when the motions like this are involved in the system, how fast the system is changing, that's a big factor, and you might not always converge to a solution. But you clearly saw that with 2, I could easily get what? I could easily get some solution here, and I was able to get some results. So, but of course, it's not biggest stress because my motion is very, very slow. But this is the essence of getting stress aligned with mechanical motions, which you can see down here. So hopefully this video was useful to you, and I will see you in my next video. Thank you.